Okay, thank you for the introduction, and also I want to thank the organizer for introducing me to talk here. So I want to talk about the structure of a package for a p-adic. So I'll just focus on the symplectic and orthogonal groups. Okay, and in this talk, I'll basically explain why we care about A packets and how we define them locally. And in the end, I want to give some examples, some concrete examples of what inside the A packets. So let's begin. So throughout this talk, I'll take G to be a SOR or a symplectic group. We assume the group is split. First, let's say it's over a number field. Okay. So the reason we want to introduce the A packets is to understand the spectral decomposition. Is that hello? Okay, yes. Okay. And so let's say we take the discrete spectrum. Okay. So we want to understand the spectral decomposition of this one. And so in our case, since we take G to be orthogonal or symplectic, we have a theorem of Arthur telling us that we can decompose this according to the so-called Arthur parameters. Okay. And then we have the Arthur packet. Then we are summing the representation in the packets with certain multiplicity. Now, the first term is over the so-called discrete global Arthur parameters. Since I'll talk about its local analog, so I will now introduce this one here. The second one is the so-called the global A packets. And in Arthur's theorem, this is a multiset. It's a multiset of admissible representations of this p-adic group. Okay? And then you are not summing all of them, so you have these multiplicities, and this can be 0, which means that this will not show up as an automorphic representation. So what's important for our talk is if you look at this global A packets, you can decompose that as a restricted tensor product of this local analog. Okay. So this will be called the local A packets. And again, this will be multiset. So these are multiset of irreducible representations of the local group. Okay. So the main goal of this talk is to understand this local packet. For this, for non-Archimedean place. So that's our goal. So now I'm going to take F to be p-adic. We have the global kind of motivation for introducing these A packets, but in being able to describe this, it's better to have a local categorization. So now I'm going to introduce the local A parameter. So it's a V group cross 2 copies of SL2C, and mapped to the dual group. In this case, this dual group will either be symplectic or orthogonal, so it has a standard representation. So we map into subterm GLNC. Okay? And then you can view this parameter as an n-dimensional representation. And as a representation, we decompose this as its irreducible subrepresentations. So the irreducible subrepresentation will decompose this as tensor product like this. Okay? So here, this rho is the irreducible unitary. So here, it's part of the condition for A parameters that we want the image of the V group to be bounded. So this rho is a unitary irreducible representation of the V group. And by the local Langland correspondence, this will correspond to some unitary irreducible Hilbert-Classical representation. Of some general linear groups. And for simplicity, I'll still denote that by rho. And then we have this nu A and nu B. So these A, B are integers, and we write nu M to be the symmetric power representation. And in particular, nu M will be the m-dimensional representation of SL2C. All right. So from this parameter, we want to build an A packet. But first, we can construct a self-dual representation of general linear groups. Okay, as follows. So I'll denote this representation by pi sub GL sub psi. Okay. So what do we have? We have a rho and we have AB. So how can we come up with a representation with these informations? So we take rho and we take A and we form the so-called Steinberg representation. So that's a representation of some general linear groups. And then we have another information B. So we use B and this representation to form the Spade representation. And again, this is a representation of some general linear groups. And now I vary these triples, rho A, B. Each of them give me a representation of some general linear groups. And altogether, they will form a representation on the Levy subgroup of some bigger general linear groups, which is GON. And then I do the parabolic induction. So I'll use this notation. Okay. And this gives me a self-dual representation of GON. So for later purpose, I would like to say a little bit about this Spade representation. So first of all, what is this Steinberg representation? It's coming from an induced representation, which I write like rho twisted by some unramified characters. Okay. So rho is a Hilbert-Classical representation. I twist by an unramified character, which is basically the determinant, and you put the actual value. Then I raise the power to a minus 1/2. Then as I go, each step I decrease the number, the exponent by 1 until I get negative a minus 1/2. Okay? So I take this induction, and then I take the soccer which is the sum of all its irreducible subrepresentations. And in this case, it has a unique irreducible subrepresentation, and that is the Steinberg. And to form a Spade representation, you just take this irreducible representation, and again, you twist by some unramified characters, where you raise the power of this absolute value to a certain number which is related to b. Okay? So here, if we keep track of these exponents, so I have a minus 1 half, and it's decreasing to negative a minus 1. And now I twist according to this b. So I'm going to add, so I'm going to add a negative b minus 1 half. So this will be b minus 1 half, okay? And then I'll keep adding. So at each row, I'm going to increase this number by 1. So eventually, I'll get b minus 1 half plus a minus 1 half. Okay. So that's how I twist according to this b. Then I just put a bracket, and that will correspond to this Spade representation. So later, I'll use this notation for the Spade representation. So it's like a matrix. And you see these exponents. So they are increasing in this direction in the rows, and in the columns, it increase in this direction. OK. So once we have this representation on general linear groups, then it will determine an A packet on the orthogonal asymplectic groups. And again, that's a theorem of Arthur. Okay. And here I'll just say very vaguely that so the corresponding A packet is actually determined by this representation on the general linear groups. Okay. And so how this is determined? So I'll just say in words. So this is a self-dual representation, so you can define so-called twisted characters. And there's a relation between certain stable linear combination of characters here with this twisted character. And that's the so-called twisted endoscopy theory. And in particular, this will determine this as a characters. So by the linear independence of these characters, it also determines this. You can say it's the multiset. And indeed, so by theorem of Mergelin, that this is actually a subset. Of the irreducible representations. Of this local group. So that's due to Mergelin. Okay. So once we know this is a set, then certainly we have to know what's inside this set. Okay. So that's the main goal of this course, this lecture. And to be able to say what's inside there, first we need to be able to parameterize the representations so that we can talk about what kind of representation will be in this packet. Okay. Okay. So how we parameterize the irreducible smooth representations for this local group. And the answer is to use the local line correspondence. And again, I'll say that the theorem of Arthur. It says that, so if we look at all the irreducible representations, then there's a bijection with set of pairs phi epsilon, and this phi is a length parameter, and this epsilon is irreducible representations of S phi. So S phi is defined in Mark's talk as the curly S phi. So it's basically the component group of the centralizer of this length parameter modulo the center of G hat. Okay. So that's how we parameterize every irreducible representations. Okay? And because of this, we can write the irreducible representations here as pi phi epsilon. Okay? And phi epsilon will be its parameter. Okay. So now I'll talk about how to describe things in a packet. And this talk will just be looking at one special case. So again, I'll write down the parameter in the form of its irreducible component. And I'll index them from 1 to R. So each component will be indexed by this I. Okay? And I say this is a special case, so I need to put some conditions. So the condition will be, if you look at the second SL2 and the corresponding representation, so presumably it will be nu B, nu Bi, so it can be different, but here I want to fix this. So I just let AI vary and the B will be fixed. So that will be the case looking at. And why this will be interesting. So suppose you think about this as a global parameter. And globally, if you decompose in this way, each component, you will just have 2 p's, because this part will corresponding to the so-called hypothetical length group, and then the second part corresponding to this SL2C, which is the second SL2C we see in the local A parameter. Okay? So globally, you only see 2 p's. And while globally, suppose in this direct sum decomposition, you only have 1 component. And that corresponding to the case when the automorphic representation globally is not endoscopic. Okay? So if you take a global parameter like this, and you decompose locally, then you have something like this one, where for the second SL2, this representation is always fixed. Okay? So in other words, this will actually give you the local component of a non-endoscopic automorphic representations. So it will be in this form. Okay. So in order to present the results, we need to make some further simplification. First, I'm going to take all these rho I to be trivial. Okay. And secondly, I'll take these AI and B to be all integers. Okay. So after this 2 simplification, we can rewrite this parameter, and now we can just forget this row. So you will just have this new AI tensor nu B. Okay. And that will be our parameter. Okay. So you think about this. The parameter is basically of combinatorial nature because we take rho to be 1, and all the arithmetic information is in rho. And since we take it to be 1, there's no arithmetics. And you can think these are just combinatorial data just by AI and B. Okay? And to understand these combinatorial data, we do a transformation. And this was given by Mergelin. We turn this into capital AI, BI, and ZI. Okay. So how to do the transformation? This capital AI is small ai plus b half minus 1. And this capital BI is the absolute value of ai minus b. Take 1/2. So since you take absolute value, you lose some information. So this ZI is going to be the sign of ai minus b. Okay? And in case ai is equal to b, you can take either plus or minus. It doesn't matter. Okay? So we turn this into these triples. And the way you think about this triple is we can just draw them in the real line. So it gives you 2 points. One is AI, the other is BI. So it distinguishes an interval. Okay? So each pair corresponds to an interval like this. Now, just to make this more visible, I'm going to draw an arc above that. It's just to make it more kind of easy to see. In particular, when you have more these pairs and you draw them in its real line, they will have like a lot of intervals and they can just intersect each other. So when you draw the arc, it's more easy to see them. Okay. And we have a zip line. Okay. So that's kind of a picture how you think about an A parameter. It's just these intervals. And so it's tempting to think about the simplest case when you just have one interval. So that will be just nu A tensor nu B. And here we make assumption that this A is bigger than B. Okay? So you have this ZI to be plus. Okay. So this is the simplest kind of example, non-trivial example for an A parameter. So what about this A packet? So I think this is really the breakthrough to kind of decoding the A packets. So before it's very mysterious. Even we have theorem of Arthur, we don't know exactly what they are as like irreducible representations. So this is theorem of Mergelin. And it opens the door for us to understanding all these sets. So I'll state this as 2 parts. So the first part is it gives the bijection between this set and the pairs where this L is valued in natural numbers and this eta is just a sign. Okay. And we have the conditions that this L is between 0 and, okay, so A minus B half. And also we need to put some sign conditions. And I'll talk about that later. So the sign condition, briefly, is corresponding to choosing the split group. Okay? So if you allow in the form, then you can drop this sign condition. Okay. So in any case, from this statement, you can tell how many representation in this packet is basically corresponding to choosing L and eta. So this eta is just a sign. Okay? So this somehow reminds you about the characters for when you describe a temporal L packet. So it's the characters for the centralized of a parameter. So that's somehow in this eta. But this L is something special for these A packets. So this L is basically telling you how long. So it's depending on how long this interval is. But Mergel's theorem is more than that. It actually tells you how you can write down the representation in this packet in terms of their length parameters. Okay, so how to write that? So now for every representation here, it's parameterized by L and eta. And usually people write this as a length quotient, but now I'm going to write this as like a sub-representation. But it's the same. Okay, so to write this, first we'll have a matrix. So as we see before, this is corresponding to a Spade representation. Okay. So that's a representation on some general linear groups. And then we have a discrete series. And it's actually on a group of the same type of G, but of smaller rank. So I call it G prime. So it's a discrete series. Okay. So how to describe this discrete series? So notice that we have its length parameters. So we just need to describe its length parameter. And so for this phi prime, again, we decompose like we decompose the A parameter. It will be in this form. Okay. So on each component, the second SL2 will be trivial, the representation for that. And the first one will have dimension 2c plus 1, where the c goes from b minus L to, b plus L to A minus L. Okay. So if we also kind of draw this parameter in this real line, then all these components, since the second one is trivial, you will see they just corresponding to points instead of intervals. And these points will go from B plus L up to A minus L. Okay, so C will just range in these intervals. And what about this epsilon prime? Okay. So that's supposed to be the character of the centralizer of this phi prime. And since we decompose phi prime in this way, this epsilon prime actually can be described as assigning a plus minus for all these integers in this interval. Okay? So in the first integer, b plus L, we're going to assign eta. And then you will just assign the sign alternately, so alternating. So at C, it will be -1 C minus B plus L eta. And you just keep going. So all these are alternating. And from all this information, actually, you can read out the length parameter for these representations. Okay? Okay. And as a remark, so here we have this pi prime, which is a discrete series. Okay? And, well, you write down it's a reducible component. They are just integers in this interval. But if you just take this interval, you realize that it's also an A parameter. And if you just go through this theorem, you see that this discrete series is actually in an A packet where the two endpoints is these two. And in this theorem, you just take L to be 0, so you don't have the first part. And you're just left with this discrete series. So in other words, I can write this discrete series okay, as a representation in an A packet. And the L will be 0 then, and eta is the same. Okay? So I'll just introduce this new notation for these particular representations. All right. So that's a special case when you just have one intervals. So now I want to talk about the case when we have more intervals. And in fact, if you have more intervals and they don't overlap with each other, then you can just copy Merkle's theorem, but then you will just see more matrices. And then also here you will just see more intervals, and you take integers among these intervals. And that's exactly the representation inside these A packets, when you have more intervals that don't overlap with each other. But in our case, you will see these intervals do overlap with each other. Okay. So in our case, we have this B fixed. So we can just index this AI so that for I is less than or equal to M, all these AI, I want this to be smaller than or equal to B. And then for the rest, it's bigger than B. Okay. So the consequence of this is for all I less than or equal to M, so this AI is less than B, and according to our transformation rule, you will see these intervals, they are all centered at B minus 1/2. Okay, so that's for I less than or equal to M. And for I bigger than M, these AI are bigger than B, so their feature is they all have the same length. The length is B minus 1. Okay. Yeah. So they all have the same length. Okay. And in particular, you will see that these plus intervals will be bigger than the minus intervals. Okay. So that's a picture. Okay. So our first result is how we are going to understand the A packet in this case. So we need to introduce a new parameter. So let me call that psi prime. And it's obtained from this psi in the following way. So again, we just need to describe all its triples. No, so it's just need to describe this AI prime, BI prime, and ZI prime. Okay? So these corresponding to the irreducible component of this psi prime. Okay. And the way we introduce this new parameter is to keep all the positive intervals, and then you kind of push all these negative intervals to 0, so their left endpoints will reach 0. And that's how we get these new parameters. So for this I is bigger than M, they are all the same. And for I is less than or equal to M, what you do is you take AI minus BI, that's the right endpoints, and then 0. Okay? And moreover, you're going to take the sign from minus to plus. So here, it's also plus automatically. Okay, so the picture will look like this. So all these negative intervals, they will have left endpoints at 0. And now they are plus, and then all the plus intervals will stay the same. Okay, so that's the picture. So the result is you will have a bijection between the original A packets and the new packets from this new parameter. Okay. So if we write pi goes to pi prime, okay, then we can also describe this pi using pi prime. And that is, this pi will be sub-representation of the following. So again, we're going to write some matrix. And now this time, there will be M matrix. And then you have pi prime. And in fact, this will be the unique irreducible sub-representation of the right-hand side. Okay. And finally, we still need to determine this pi prime. So let's just look at the corresponding A parameter again. And you will notice that for this new parameter psi prime, it has a property that all these AI prime is bigger than or equal to AI minus 1 prime, and BI prime is bigger than or equal to BI minus 1 prime. Okay. And also all these sign is positive. Okay. So that's the feature for this new parameter. And indeed, for all these kind of parameter with this property, we can describe everything inside them explicitly. So this is the second main result. So just like Merkle theorem, we have a bijection between this packet and pairs. But now since we have more intervals, so this L lower bar is going to be like a tuple of R entries. And similarly, this at lower bar. Okay. So what are the conditions? So first of all, for each of these intervals, we want Li to be between 0 and AI minus BI half. Okay. And then for the eta, so if we have this eta I plus 1 is equal to half AI prime minus BI prime eta I, then we want this the following to hold. Okay. And so if we have these two signs are not equal, okay, and then we have a condition that this BI plus 1 plus AI plus 1 is strictly bigger than this AI minus Li. Okay. And then we have some sign conditions. Okay. Yeah, so that's the condition. So from this part, at least you can tell how many elements in this packet. Okay. But moreover, we would like to describe explicitly what are these representations. So how much time do I have? 13? Okay. Okay, so to describe this, we need more space. So first of all, just like Merkle theorem, we'll have some matrices which just coming from each of these pairs, L and eta. So this pi prime parameterized by L and at the lower bar. So it is as a sub-representation inside the induced representation. Okay, so to write down the induced representation, first you have some representation of general linear groups. Okay, so that part is exactly the same as Merkle's theorem. You have these parts. But the next step is where the difficulty comes from. So maybe I'll just describe it here. So remember that in Merkle's theorem, after we're taking out these matrices, we are left with, say, is A minus L and B plus L. Okay? And we simply taking integers in this interval, and that will give us some discrete series parameters. Okay? So that's the case when you just have one interval. But this time you have more intervals, and if they don't intersect each other, again you take their integers among them. But what happens if they do intersect with each other? So that's where the difficulties come in. So here, just for example, suppose we have these two intervals. And so you can see on this picture that they kind of do intersect with each other. So what can we do to separate them? So the kind of philosophy or idea is you look at these two endpoints, okay, from these two intervals. And for the right one, you hope you can just draw it to the left. And for the left ones, you want to kind of push it to the right. And you do it simultaneously until they both cross or hit the middle points. Okay? So I'll just denote the middle point by Ti. So it's half Ai minus Li plus Ei plus 1 is plus L plus 1. Okay. So that's how you separate them. And whenever you see a situation like this, and you try to let these 2 points kind of go in opposite directions, then you will produce another matrix. Okay. So for simplicity, I'm going to make the assumption so that all the intervals you see will intersect with each other. Okay, so that's easier to write this second one. So the assumption is that I want all this. Okay. This condition to hold, so they do intersect. Okay. Then, so how many? So for each consecutive intervals, so there will be like I minus R minus 1 pairs. Then they will give you a matrix. So this is Ti minus 1 and negative Ti plus 1. Okay. So that's coming from you separating these two. And finally, once you separate this, and you can just take what's left, and then you take all the integers. So in the end, you get, hi. And remember that we write them as like coming from, okay, Okay, so coming from like a parameter or a packet, but we take L to be 0. And then for this sign, it is Ti minus 1 minus Gi prime plus Li. Okay. So just have more. Okay. So that's under this assumption. And if you don't have this assumption, then you only need to take out a matrix when you see this intersection. And then you just take the rest of the intervals and you count all the integers. Okay? And in particular, so what's this one? So in Mergel's theorem, you always get a discrete series. But here, you will get a temporal representations, meaning that they can have multiplicities. Okay? All right, so I'll stop here. What's the theorem? A formula for just for the size, for the cardinality. Yes. So in general, if you take an A parameters, so just for I think this part of the theorem. So in general, you can describe the A packet in this way, and that's actually due to Mergelin. So she's able to describe all the p-adic A packets for classical groups by pairs of this, but with some conditions. Okay, and that's not with. I think that's something not in Mergelin's original work. She didn't describe these conditions, so she just described this. But the conditions is determined by some kind of like vanishing condition on the Jacquet restriction. So I have an early work which is to basically deduce these conditions, and it's more like an algorithm. And eventually, you go through the algorithm, and you end up with something like this. So these are kind of like a linear constraints on these Li's. Okay? So you think that you fix these eta I, and then you look at this Li. Originally, they kind of in this like R-dimensional box, and you count all the integer points. But then to get this packet, you have to impose some kind of linear constraints. Okay? And that will cut your box. Okay? And then after you put all these constraints, and then you count the integral points in this probably convex solid, and that will give you, but we don't have a formula. Yeah. So there's a way to count, but not formula.